Hey everyone, Miss B here. So in this video we're looking at the unit for lesson 16 cumulative practice problems, and this is for Illustrative Math Algebra 1. So starting off, we have tickets to a family concert. They cost $10 for adults and $3 for children. The concert organizers collected a total of $900 from ticket sales. So in this situation, what is the meaning of each variable in the equation 10a plus 3c equals 900? Well, it looks like to me they have a price, and then we would normally multiply that with the number of tickets that were sold. So that looks to me like $10 for adults, and then the 3c is the $3 for children. So the a and the c are actually not the price because the prices are included there. The A is the number of adult tickets, and the C is the number of child tickets. So we're going to say A is number of adult tickets sold. And then we're going to say that C is the number of child tickets sold. Okay. So part B says, if 42 adults were at the concert, then how many children attended? So this is actually giving us a value to plug in for A. And so we're just going to calculate that. 42 adults, so they're saying that A is equal to 42. We're going to use that number and plug some stuff in. And actually, do I have some space to show my work? I might have some space to show my work off to the side, just to kind of show my calculations. I like to do some of this a little more vertical. So I am actually going to use the original equation they gave me, which is 10a plus 3c equals 900. And then they gave me that A was 42. So 10 times 42 plus 3C equals 900. So this is 420 plus 3C equals 900. We want to subtract this from both sides because we are trying to get the C by itself in order to figure out how many kids. So these would cancel each other out and just leave us with 3c. And then I want to double check myself with a calculator just because I don't trust myself with subtraction. I'm still a little bad at it mentally. But 900 minus 420 is 480. And then if we take 480, that's equal to the number, that's actually the amount of money that they got from the children's tickets. But we want to know how many children's tickets, so we need to divide by 3 on both sides. This is going to give us that C equals, C is equal to, I believe, 160. Let me check myself on that. 480 divided by 3. Yep, 160. So this is the work I was kind of showing for that. C equals 160. So that's how many children attended. 160 children attended. Okay. If 140 children were at the concert, how many adults attended? So I might show some of this work over to the right since I showed my work for this other one over to the left. So they're saying, in this case now, C is equal to 140. And they want to know what A is. So we're still going to use the original function, which is 10a plus 3c equals 900. But now we're saying 10a plus 3 times 140 is equal to 900. So we're plugging in that value, and I'm going to zoom in over here so you can see my work a little better. Okay, so doing 3 times 140 is going to give us 420 again. So 10a is, 10a plus 420 is equal to 900. And if we subtract that from both sides, we're still going to get the same answer as we did previously, which is that 480. We're just now going to be dividing by a different number. So these will cancel right here, and we're going to have 10a equals 480. And if you divide both sides by 10, all that does is move your decimal point one place, or in this case, it's going to knock the 0 off of the end of that 480. Tens will cancel here though, so we'll get a is 48. So my answer is that 48, or a equals 48, so 48 adults attended. There we go. Okay, now D and E, they're really giving us a whole lot to do on this assignment. Already multiple pieces to this one problem, but we can do it. Write an equation to represent C as a function of A, and explain what this function tells us about the situation. So, the number of children and the number of adults, we want to write ourselves a function. So, we can manipulate our original function, and I'm just going to show all of that work here. So we can say 10a plus 3c equals 900. Now we don't have anything we're plugging in, but we're going to do the same idea of getting c by itself. So that means I'm going to subtract 10a from both sides because I want it to go away. So I would have 3c is equal to 900 minus 10a. And then I have to divide that entire thing by 3 because I have to divide both sides by 3. So this whole thing gets grouped, being divided by 3. So my function for c is... and you don't have to simplify this because 10 doesn't divide by 3, so we can leave this as 900 minus 10a over 3. Okay, so now we need to explain what the function tells us about the situation. Really just what the function is. We're saying function c gives... So it's giving an output number, right? The output is the number of children who attended. And this is as a function or when a certain number of adults attended. So attended, I'm going to say as a function of the number of adults who attended. Basically, if I know A, it allows me to plug A in and get C. So now we're going to do part E, which is to solve for the other variable here. So we're going to still use 10A plus 3C, and that's equal to 900. But now we're looking to get A by itself. So we're going to subtract 3C from both sides. So we want that to go away. So now we would just have 10a equals 900 minus 3c. We're going to divide both sides by 10 to get a all alone. So this means that a is 900 minus 3c and then divided by 10. So we want to explain what this one is. It's basically the opposite of our other one. So this, we can say function a gives the number of, and we can even just say adult tickets sold or adult tickets when we can say when C number of children's or child tickets are sold. Or were sold, it's in the past, were sold. So two different ways that you can kind of say the same thing. I used part D, I wrote a more formal one. I said it gives the number of children who attended as a function of the number of adults who attended. It's the same thing as if I said it gives the number of tickets when such and such number of tickets were sold, which is what I'm saying here. Although we do have our inputs and outputs reversed, so these are inverses of each other. Problem 2. So a school group has $600 to spend on t-shirts, and the group is buying from a store that gives them a $5 discount off the regular price per shirt. So we have two things here. We have n equals 600 divided by p minus 5, which gives the number of shirts, n, that you can purchase at regular price, p. We then have p equals 600 divided by n plus 5. That gives the regular price p of a shirt when n number of shirts are purchased. So we have two questions. What is n when p is 20? So if we want to find n, we're going to use the one that is solved for n, because then we would just plug in p and simplify this thing right here. So let's do that. All right, we're going to say n equals, and p is 20, so this is 600 over 20 minus 5. So I'm just going to move laterally here. 600 and 20 minus 5 is 15, so now we're just doing 600 divided by 15, which is 40. So n is 40. So when p is 20, n is 40. So if the regular price is 20, they can buy 40 shirts. Now, what is p when n is 40? We're going to take 40 and plug it in. We're going to use this one here where it's already solved for p, and then we'll show our work here. So we're going to say, you know what, and I'll do this where I do my work in red. That way it doesn't quite get mixed up with my other work here. So p is 600 divided by the n number of shirts, and then we're going to add $5 to that. So in this case, n is 40, so we're going to have 600 divided by 40, and then plus 5, which, you know what, I can show my work going down here. I have room. Sorry, I kind of last second decided I'm doing this way. Okay. And then 600 divided by 40 is going to be 15, so this is 15 plus 5, so P is equal to 20. And that price is $20. So, there is a third part to this question, I believe, and that is, yep, on the next page. So they're asking us, is one function an inverse of the other, and explain how we know. So yes, first of all, yes they are. And we're going to kind of use the idea that we could solve each of them for each other and they would give the same equation, but if the input of one gives an output and then we stick that output, so we're given an input of P here, which gives us an output of 40. If we then take that output and plug it into what we believe is the inverse, it should give us out the original amount we plugged in to start with. So it basically takes us full circle. We're starting with $20. We're finding out that's 40 shirts. We're then taking 40 shirts and plugging that in, and we're finding out that's $20. So we've just gone in a loop. And that whole idea of those two prices and amount of shirts, I suppose, that those create a loop, shows us that one equation undoes the other. So that was a lot of words for me to just say. I'm actually going to do some writing here now. So we can say the inputs and outputs are reversed. We can also say, yeah, so we'll start with that. We'll say, yes, the inputs and outputs are reversed. And then we can say what I kind of described on the other page, which is plugging the output of one into the other gives the original input, which is a long way of saying they undo each other. Okay. All right, so on to question 3. Oh, look, a nice short one. So we have functions f and g are inverses, and then they give us the function of -2 is 3. So is the point 3, -2 on the graph of f or on the graph of g, or neither? So if we just boiled this one down, f of -2 equals 3, let's boil this down to an input-output pair. So for function f, that means when we input -2, the output value is 3. What an inverse function will do is reverse the input-output pairs. So g would take this and turn this into 3, -2. And that actually is what they're asking us. Is it on f or g or neither? So we can say this, the point is on the graph of function g. because it literally just is the input and output pairs reverse. Okay. And that it has that property because they are inverses, which they told us at the start of the question. So question 4, we're now doing some select all statements here. So we have, here are two equations that relate to quantities P and Q. So Q is equal to 7P plus 1,999. And P is equal to Q minus 1,999 and then divided by 7. So our job now is to select all statements that are true about P and Q. So the first one says this could represent a function. So Q could represent a function, but P could not. Now a function is just something that has, for every input there is only one output value. And that's not true for this one. They could both be functions, because we're not going to have something that would have multiples, and then we're actually not going to have a gap because we don't have anything where we could accidentally divide by 0. So this one's not true. Cross that out a little bigger. Each equation could represent a function. Why, yes, I just said that. So this is going to be true, and we're going to select that one. P could represent a function, but Q could not. Well, that goes against what we just selected in B, so not that one. The two equations represent two functions that are inverses of one another. Why, yes, they absolutely do represent inverses of one another, and we could actually show that work, or you could just take my word for it, but they undo each other by doing inverse operations in reverse order. So this one says, the very last option, if Q is 7P plus 1,999, if it represents a function, then the inverse can be defined by 7Q minus 199, and that's not true. They're saying 7P and 7Q. While they were right that they swapped the addition and the subtraction, we cannot maintain the multiplication there. It does have to become division. So it's not going to work on that one because we can't keep that multiplication. So yeah, it is just statements B and D that are true. If we move on to question 5, we have Elena playing the piano for 30 minutes each practice day. So the total number of minutes, P, that Elena practiced last week is a function of N, the number of practice days. So find the domain and range for this function. So they're telling us it is a function, but we're going to first identify what is our input and output. So it is a function of N, the number of practice days. So this is our input, because output is a function of input. And then the total number of minutes, which we're defining by P, is output. Okay, so finding our domain and range. So first, let's look at domain, which means we are just focusing on our input. So in a week, we have a maximum number of days. So we are going to say that domain this is allowed to be 0. She could have not practiced at all, and that's fine. But otherwise, we do need to use whole numbers or integers for this. And it can be any number from 0 to 7, as long as it's a whole number, because you can't practice more than 7 days in a week. And you can't practice half a day. You either did or you did not practice. So we can describe this as whole numbers. from 0 to 7. You could also describe that range using an inequality, but we'd still have to say that it's either whole numbers or integers. For our range, we are going to have some answers that depend. So, for each practice day, she is practicing, I see 30 minutes each practice day. So, if she doesn't practice at all, then she doesn't practice at all. So our lowest is going to be 0. But if she does practice every single day, we need to take 7 and multiply it by 30. So that is going to be 210. So the maximum amount of minutes she'll practice is 210. So this is going to be multiples of 30, because we're multiplying by 30. So multiples of 30 from 0 to 210. And that's the description for our range. And that was it for that question. So I was just checking that there wasn't anything more below it. Yeah, they just wanted us to describe a reasonable domain and range for this question. So moving on, we have question 6. So this graph shows attendance at a sports game as a function of time in minutes. Describe how attendance changed over time. So then after that, we're going to describe the domain and describe the range. The attendance, to me, looks like it's going up pretty fast. People still getting there as the game's starting, but, you know, within about 10 minutes, most people are there. And then it kind of stays about constant. Pretty much everyone's there. Then we kind of have some people start to leave, and it pauses, and then everyone leaves. So let's actually put that into words. So use my thinner pen here. So the attendance, we can say attendance increases quickly for the first 10 minutes. After 15 minutes, it levels off. We can say it levels off, or we can say it stays constant until, and this looks like about 45 minutes. Until 45 minutes, when a few people leave. Now we have this small little space where no one leaves for that little amount of time. That looks like maybe 5 minutes. So and say after 5 more minutes, everyone begins to leave. And that's at a constant rate, so you can say begins to leave at a constant rate But it's kind of implied, but yeah. So domain. Domain is our input, and this one is time in minutes. And our domain is every value on this graph from 0 all the way up until 70. So the minimum is 0, and the, well, I don't want to use the words minimum and maximum, but the furthest it goes to the left is 0, and the furthest our graph goes to the right is 70. So we can say all numbers from 0 to 70. Now it's not just whole numbers, because time, especially something measured in minutes or seconds or things like that, we can have fractions of time, and it's okay to not have whole numbers. Now as for the range, the lowest this goes is 0 people, but it looks like the highest that this goes is about 55 people in attendance. So if we have people attending, our range cannot be fractions. So our range is whole numbers or integers. And this is going to be from 0 to 55. And it is possible that there's just not people there, so 0 is an actual input and output value here. And that's the question for number 6. It's just kind of describing what that graph looks like, and then giving ways to describe our domain and our range. Question 7. 2 children set up a lemonade stand in their front yard, and they charge $1 for every cup of lemonade. So they sell a total of 15 cups of lemonade, and the amount of money they earned, R, in dollars, is a function of number of cups of lemonades they sold, which is N. Is 20 a part of the domain? So first off, they said dollars is a function of number of cups. So output is dollars, and input is the number of cups they sold. It says they sell a total of 15 cups of lemonade, which means they cannot sell more than that. So is 20 part of the domain? Domain is our input. So we can say no, they only sold 15. 15 cups. So it is not, and it's because they can't sell more than 15. So what does the range of this function represent? The range is how much money they make. So, and it's not asking us to describe it, it's just asking us what does it represent. So this represents range represents how much money. Now that would be a specific output value, but the range actually represents how much money they could make depending on the number of cups sold. So how much money they make depending on cups sold. Okay. So describe the set of values in the range of R. Well, you can't sell half of a cup of lemonade. I'm sure you could only fill it halfway, but this doesn't tell us that they have a price policy for that. So it just says a $1, 1 cup. We're going to say they have to physically hand you a cup, no matter how full it is. So that cup is going to cost $1. So that means the domain is whole numbers. And since the range depends on our domain, this one is also going to be only whole numbers. And that would be from 0 to 15. Because they could sell 0 cups, but the maximum they sold was 15. So whole numbers from 0 to 15. Is the graph of this function discrete or continuous? Now, continuous means we would do all of the things in between these different values. And since we're just using whole numbers, we're going to call this one discrete, meaning we have specific points and specific values, but not something for every point in between. So we can say discrete because can we say it doesn't make sense? It doesn't make sense to sell a fraction of a cup because you would have to give them the physical cup, because yeah, we'll just say it doesn't make sense because technically you could cut up a cup and sell it, but no one would buy that. It doesn't make sense to sell part of a cup. So it is whole numbers only. Okay, that is all for question 7. We have one more question. Now, I realize some of these questions may not be on your assignment. I don't remember exactly how long our assignment was, but if they're not, then you don't have to keep listening or watching. But we do have one more question, and that is number 8, and then this is the last one. You'll see the end of this page is kind of blank. So here is the graph of function f, which represents Andre's distance from his bicycle as he walked in a park. So we've seen Andre and his bicycle a couple times now. We're going to look at some things from this. So estimate f of 5. So that means that 5 is the input value, but we're going to estimate what the output value is at 5. So to me, 5 right here for input looks like it's about 5 for the output. So we can say f of 5 is equal to 5. Okay. Now estimate f. That's 17. So 15, this is going to be 16, and then 17, that's right here. A little bit past it is actually where our minimum is, but this looks like it touches right at one of those corners of the graph squares. So I'm going to call that 1. So I would say f of 17 equals 1. Now, they want to know for what values of t, so what time, is the function value going to be 8? So for what time is 8 and 8, this is a distance. So we're going to look at 8 specifically right here on our output value because it's a distance. And we're going to trace this across. Now it looks like we intersect 8 up here. This looks like maybe the maximum where it's 9 seconds. And if we keep going, we also have another point here and another point here. So we actually have 3 values that we're going to estimate here. So that would be I think they're actually considering it crossing right here. So if you wanted to use 9, I guess it's a little hard to see, especially on your graphs, because I know you have a small version of this. But we're going to say that this is 8.5 and then 9.5 instead of just actually 9, because it does look like it goes a little above it here. So we're actually going to give 4 values for this one. We're going to say that f of t equals 8 when t equals, and then we had 8.5. We also had 9.5. And then over to the right, it looks like we have right here, which looks like 20.5, and then right here, which is 22. So I'm going to use 20.5 and 22. There we go. They want us to now read what values of t does the function equal 6.5. So we're going to do the same thing. We're going to find 6.5 and kind of read this across. So if this is 6 and this is 7, we're going to go right across in here and try to figure out where these numbers are. Okay, let's mark on my graph. So it looks like right about here. And then it also looks like this entire portion of my graph is at 6.5. It looks like I have another spot right here and another spot right here. So we're going to estimate those values, but we're also going to have a sort of a range in there. Okay, so for this first piece, I want to say this part right here looks like maybe, what is that? That's 5, 6, a little bit after 6. So 6.5, can we call this 6.5, 6.5? Not quite. We can maybe call it like 6.2, but it's an estimate. So since it's an estimate, I'll just say that looks like 6.3 maybe. So we can say f of t is 6.5, because that was the output value we were looking at, when t equals, so we said, maybe it's around 6.3. 6.3, 6.5, you're estimating, you're reading from the graph as best you can. We have that gap. So I actually didn't measure to the sides of my gap here, but this is 11, and it looks like 14.5. So we're going to say t equals 6.3. We're also then going to say 11 is less than or equal to t is less than or equal to, was that 13.5, 14.5? 14.5. So we have t is equal to that value when we have t is in between these two values, and we have 2 more values. Oops, somehow my dot got erased there. So these 2 other dots up further on the right. So this looks like it was, we said maybe 19.5, and I think the other one's around 23.5. So, and when t is 19.5, and t is 23.5. So all of those different times we have that height, or I'm sorry, it's not a height in this one, it's a distance from his bike. Okay, so the last question is, for what values of t does f of t equal 10? So we want to know, when is the distance 10? And we don't actually hit a distance of 10. The biggest we get here is just above 8. So it doesn't, or it's undefined. So we are going to say undefined because it's not a possible output number, which means it's not in the range. It is not in the range. So it is not in our possible output values. And so this is the last question of this homework assignment. So this was from Unit 4, Lesson 16, and this was the Illustrative Math Algebra 1 practice problems for Unit 4 and Lesson 16.